ギャラリー表示にすると見えるかも。
これで十分大きさ。
そうか、自分には見えないですね。
これで大きさは十分ですか？
はい。
全画面にした方がいいかな。全画面にすると、こんな感じだけど。
こちらの方が見やすいです。
はい、
これは何で？
では始めますね。Let's start the second talk. The speaker is Shuji Saito from University of Tokyo. The title is The Abbes-Saito Formula for Motivic Ramification Filtrations.
Thank you for introductions. And first of all, I thank organizers for giving me this honor to speak this beautiful conference, and also for their big efforts to making this conference possible despite all these difficult times. So congratulations, Takeshi. So this is now a really nice conference. I'm enjoying all these beautiful talks. And actually, I met Takeshi 40 years ago. And since then, we shared so many memorable moments in life, mathematically or even non mathematically, and so many stories to tell. But since I have already given one in the party on the Wednesday evening, today I just say thank you, Takeshi, for all these mathematical inspirations and also for all your incredible kindness. Thank you.
Thank you very much.
So I start my talk. So as you see, this is very much inspired by Takeshi's works, and I'm very happy to talk about it on the special occasion. Okay, so here's a plan of talk. So first I review Abbes-Saito theories on the ramification theories, and then I review this motivic ramification filtrations, and then I state this main theorems of this talk, which is a comparison theorem of motivic and also another filtration, Abbes-Saito filtrations. And the next section, I explain some key ingredient in the proof, which is reciprocity, which is some kind of effective computational tool to compute motivic filtrations. And then next section, I give some computation of the characteristic form, which is derived from this theories. And finally, if time permits, I like to explain some application on CD, so-called CD arc descent for the reciprocity sheaves. I mean, this is some topology introduced by Bat and Matthew, and also Elmant, Hoyoiwa, Kelly, and Iwasa for the CD versions. And I like to explain some application of this result in these talks to this kind of a subject. Okay, so I reviewed the Abbes-Saito theories. So this is a non-logarithmic version. So let's X be a smooth separate scheme of a perfect field of K. By the way, I'm not so used to this, like talking to the laptop, and so please help me to ask questions. So then, like you are given some simple numerical divisor, and a complement is you, and you are given some effective divisor supporting on D, and Ni is multiplicities of each irreducible component. And then Abbes-Saito used this geometric construction called the dilatations, which is blow up of the self product of X in the center of the diagonal intersect with R cross R, and you remove strict transform of X cross R and R cross X. And then you have two projections. For first map is just canonical map, and you have two projection, and which induce two projection from PXR to the X. And inverse image of U is just U cross U for both projections. And for finite group G and G torsor phi over U, Abbes-Saito gives some condition that a ramification of this G torsor is bounded by R using this geometric constructions. And I just remarked that Abbes-Saito theory works for even for the case of the Q divisors. But in this talk, I only work with the integral divisor. And assuming G is abelian, Abbes-Saito condition is now equivalent to the following condition. Namely, so you pull back the your G torsor over U to G torsor U cross U by these two projections, and you take a difference of this. And then this G torsor over U cross U extend to the G torsor over Px of R. So that's a condition for the boundedness of the ramifications. So this defines, so this is a group of the G torsors over U, and this defines some filtrations on these groups by these conditions. And so this filtration is parametrized by XR, pair of XR, where U is actually, I forgot to say, I put this slides in my personal web page. So you can find it, this slide in the personal web page. And there is a section for the preprint. And on the last part of the section of the preprint of personal web page, I put this in like slides. So you can find it here if you like. Okay, any questions so far? Okay, then Takeshi constructed so-called characteristic form, which appeared also in this Yatagawa's talk. So which looks like this. For simplicity, we assume G is cyclic, and P is not P is odd, and multiplicities of the component in this ramification divisor is greater than 2. Then this characteristic form looks like this. So you have this subgroup of the G torsors, like for G torsor bound, whose ramification is bounded by this R, and target space is the global section of the sheaves. So these are support of the ramification divisor R. And the construction goes as follows. So first, you observe the this PXR is vector bounded over D. And then you look at this map from the Abbes-Saito, this filtration to this D torsor, group of D torsor of the dilatations given by this, like difference of the pullback by two projections. And by definition, this extends to this D torsor over this dilatation. And then you restrict it to the VR. Okay, so then you can show the image of this map is lies in the so-called like additive part of this group of G torsor over VR, which satisfy these conditions. Okay, then Takeshi shows the this any element in this subgroup of the additive element of the G torsor is given by just Alten-Schreier covering of this form. So that's how you can get this characteristic form like this. And here is some main result from Abbes-Saito theory. So first result is Zariski-Nagata parities. And so this tells you that this Abbes-Saito filtrations is determined by the Abbes-Saito filtrations for the Henselization. So this is a Henselization of X at generic point of the this ramification divisors. So that's kind of a Zariski-Nagata parities. And also Takeshi proves this characteristic form. Okay, so given some ideal component with multiplicity greater than 1 and a dense open, if you restrict this characteristic form to the B, kernel is exactly those torsors whose ramification is bounded by the smaller divisors. Okay. Any questions so far? It's okay. And next result I have to mention is some explicit computation of the characteristic form. So here we assume the X is affine, and D is some principle given by pi equals 0, and then by Alten-Schreier bit series. So this group of G torsor over U is just given by this, like bit vectors modulo 1 minus f. And so Abbes-Saito and also Yatagawa compute this Abbes-Saito filtrations for this pair explicitly by using this brilliancy Kato-Matsuda filtrations, and also the compute characteristic form in this by this very explicit form. Actually, this appeared in previous work by Kazuya Kato on his work on the refined Swan conductor. Okay. So I just wrote this brilliance Kato filtration and the Matsuda's variant, but well, anyway, so it's a bit complicated to explain, so I just skip it. Okay. So now, like so any questions so far? Chat. Okay. Okay, so it's no questions. Okay. Okay, so now I move on to the motivic ramification filtrations. So in the rest of the talk, I fix a perfect base field K, and okay, so this one is a separate category of separate schemes, and this one is a category of smooth schemes of finite type. This is essentially smooth schemes, and given some pre-sheaves on smooth schemes, we can extend it to the like a smooth tilde by this formula. So when this essentially smooth scheme is written as a limit of the some smooth schemes where all transition maps are eternal, so you just define this as a filtered limit, colimit like this. Okay, that's kind of a standard notation. And then so for example, like we can take this like Henselization of the smooth scheme at some point. And then we also use the following categories in play. So this is category of the pair where X is schemes and R is an effective Cartier divisor whose interior is smooth. And this guy is subcategories where X is not proper. And also for fixed smooth scheme U, we have this we call the modulus pairs. So this is a category of modulus pair whose interior is U. So this is proper modulus pair. So this is non-proper modulus pair whose interior is U. Okay. Now, fundamental constructions due to Kan, Yamazaki, Miyazaki, and Yamazaki is the following. We have these two functors like this. So where this is a category of the pre-sheaves of the abelian group on smooth schemes with transfer, which I'm going to explain in a moment. And this, you have functor to the pre-sheaves. You can kind of upgrade this pre-sheaves on smooth schemes to the pre-sheaves on this pair, proper modulus pair. And then you can kind of left can extend to the pre-sheaves on the non-proper modulus pair by the inclusion over here. Okay, so here is the definitions. So this you introduce the category of the finite correspondence whose objects are the same as the smooth schemes, and morphisms are finite, so-called finite correspondence, which are finite integral sum of the elementary correspondence, which is so for elementary correspondence from X to Y, X and Y are smooth, is irreducible closed subset in X cross Y, which are finite and subject to over component of X. Then taking graph, we get the functor from the this category of smooth schemes to the category of the finite correspondence. Okay, and then like this my main player in this talk is a category of the additive pre-sheaves on this category of the finite correspondence. Okay, any question on this? It's okay. And then we use representative object. So in these categories, so this is represented. This is a pre-sheaf with a transfer represented by this smooth scheme U. Okay, then Yoneda lemma says they are for pre-sheaf transfer F and smooth schemes U. Fu is identified of the home group in these categories from this representative object to F. This is the unit lemma. Okay, then idea to define the this is like a subgroup of the FU for this pair associated for this this compactifications of U is the following. So we just define this as a home group in these categories from the some quotient of this representative object attached to this pair. And this quotient is defined as follows. Okay, for take any irreducible smooth schemes with generic point, then by definition, this value of the this representative object on T is the subgroup of the zero cycles on this U cross E. So this is a generic fiber of U cross T, satisfying the condition that the closure of the support is finite over T. Okay, that's by definition. Okay, then this guy valued at like a T is image of the these things embedded in this group of the zero cycles on this generic fiber of this guy, and you go down to the so-called Char group of zero cycles with modulus. So this guy is quotient of the group of zero cycles modulo these relations. So this is a divisor of the functions on curves on this U cross eta, generic fiber of the U cross T, where F ranges all over all rational function on this curve, satisfying this congruence relations. And where this C bar is the closure of C in X eta, and C bar N is normalizations, and this is the product of the divisor, given divisor of X to the this C bar N. So this gives us some kind of a generalization of the child group of the U eta. Okay, I mean, I have to confess I cheated a bit. Actually, this description of the this thing is valid only locally on T, but never mind. So then anyway, so by this we get this like a functor from the press sheaf with transfer to the press sheaves on the category of the proper modulus pair. And about this transfer structure, I'll explain you later. Okay, then, okay, this second functor is rather formal and the categorical constructions. This is a kind of a left-hand extensions along this inclusion of the category. So this is a category of the proper modulus pair, and this is category of non-proper modulus pair. And you have very categorical formal construction of the left-hand extension. Okay, so because I running out of time, so maybe I just skip this explanation, but of this left-hand extension. But this is really very formal. Okay, any questions so far? Okay. Okay, so then we get this in like two functors. Like so, this is very essential, and this is a very formal and categorical constructions. So for simplicity, we write F tilde for this image of F in over here, and this I recall that this gives for any smooth schemes and like some filtrations on this FU parametrized by this partial compactification of the smooth scheme U. And I explained this transfer structure over here. So this is equipped with so-called functoriality is called like modulus transfer. So which goes as follows. So given another smooth scheme V and its partial compactification Y and S. So and also given some finite correspondence from B to U, okay, and which by definition induce map from FU to FV. So this map, induced map, sends this motivic filtration to the motivic filtration on V under the following two conditions. first condition is the closure of Z. So Z is the V cross U, and you can take the closure in Y cross X, and this should be proper by Y. And the second condition, which is more important, is that you can pull back of the divisor of R on X and the divisor S on Y to the normalization of the disclosure. So, and we demand this inequality of the divisor on Z bar N. Okay, that's the kind of a extra kind of a functoriality we have for this, like motivic filtrations. Okay, any questions so far? Okay, now I defined the reciprocity sheaf. So pre-sheaf with transfer is reciprocity sheaf if the restriction of F to the category smooth scheme is Nisnevich sheaves. So the sheaf on the Nisnevich topology on the category smooth schemes. And the second condition is so for any given smooth schemes, you have this motivic filtrations parameterized by the compactifications of U. So this is a proper modulus pair whose interiors are U. And we demand this filtration is exhaustive. So heuristically, this tells that any section of FU has bounded ramification along the compactifications of U. So that's the conditions. Okay, then so we have this full subcategory of the reciprocity sheaves, and some important result is this category is Grothendieck abelian categories. Point is this mismatchification on this category preserve the reciprocity. Any questions so far? It's okay. Okay, so now I give you some examples of the reciprocity sheaves. So first example is the A1 invariant sheaf, Nisnevich sheaf with transfer on the category of smooth scheme. For example, like multiple category groups or Milner K sheaves. And actually, one can show that this Nisnevich sheaf with transfer is A1 invariant if and only if this motivic filtration, it only depends on the support of R, like this. So heuristically, it says, so this pre-shift transfer is A1 invariant if and only if F is temporally ramified along the boundary. Okay, that's the first example. And the second example is Kähler differentials and also cohomology sheaves of the Duran complex, and also Duran bit sheaves or the block Durini-Illusis is also reciprocity sheaves, and also sheaves represented by smooth commutative algebraic K group is also reciprocity sheaves. For example, like additive group, and also group of the connections of the isomorphic class of the connections of rank 1 is also reciprocity sheaves. And also a group of the isomorphism classes of the QL bar sheaf of rank 1 is also reciprocity sheaves. And also the group of the flat FPPF torsor for the finite flat K group schemes is also reciprocity sheaves. And another example is the higher direct image for the this change morphism of change of side from et al. Topology to the Nisnevich topology of the so-called et al. Motivic complex with cumulative coefficient, which is completely sum of the Tate twist of the roots of unities, and in a positive characteristic, we have to add some shift of the logarithmic part of the Duran bit. And example, for example, like H10 is the dual of the abelianized fundamental group. H21 is a cohomological Brouwer group, and Hn plus 1n is unramified cohomological. Okay, any question so far? It's okay. And indeed, we can, out of all these examples, we can manufacture more examples using, okay, first of all, like this category is abelian, so you can take in some kernel and co-kernel of some map. So for example, like a sheaf of the exact form, or closed form in Kähler differentials also refers to sheaves. And also this category carries some tensor structures defined by Rülling, Sugiyama, Yamazaki, and also internal home structure. So using these like structures, one can manufacture some new reciprocity sheaves out of known ones. Here are some examples of this tensor product. So for example, GM, tensor GA is omega 1, and GA, tensor GA is, this is the first infinitesimal neighborhood of the diagonal. And also some similar formula, some kind of for the internal form in category of reciprocity sheaves. Okay, any questions so far? Okay. Okay, I just summarize, because this section is rather long, I just summarize content of the sections. So we have construction of the functor from the pre-sheaf with transfer to the pre-sheaf with transfer on the category of the non-proper modulus pair, written like this. So this gives us some motivic filtration on the section of the given pre-sheaf transfer over some smooth scheme U, parametrized by this partial compactification of U, and which satisfy some functorialities called a modular transfer. And we define F to be F over here, pre-sheaf transfer to be a reciprocity sheaf, to be if F is a sheaf on the Nisnevich side of the smooth schemes, and this filtration is exhausted. Okay, that's a summary. And one remark is the, okay, this Char group with of zero cycles with modulus used in the definition of this motivic filtration is very hard to compute. So it seems hopeless to compute this motivic filtrations just by definition. So it's desirable to invent some effective tool to compute it. And this is what I will be explained in the next section. Okay, so any questions so far? Okay, so this is a comparison theorem of the motivic and Abbes-Saito filtration. So here's a notation. So we fix the some modulus pair, so where X is smooth and R is some effective Kato divisor on X, but we assume support D of this R is some simple normal crossing on X. And we introduce some terminology. So this, we say this XR admits smooth compactification if there exists some open immersion where X is smooth and proper, and complement of this interior of X of this guy in X bar is simple normal crossing on X bar. For example, this is a case if X is, this X is already proper. So if X is proper, this is just unconditional. Okay, so first result, which is motivic version of the Zariski-Nagata parities, it tells you that this motivic filtration just introduced is also determined by the motivic filtration of this Henselization of X at generic points of the ramification divisor. So this is a motivic version of the Abbes-Saito theorem on this kind of parities for the group of the G torsor. Any question on this? So that's first result. But real main result is the following. So recall we had this like Abbes-Saito construction for this pair. So X is smooth and R is effective calculated divisors, and I use the interior, and you have this PXR called like dilatation, which is a blow up of X cross X in the center of the diagonal intersect R cross R. And you have two projections and whose inverse image is just U cross U. In these situations, we just defined Abbes-Saito filtrations for the reciprocity sheaf as exactly same manner as Abbes-Saito's ramification condition. Namely, we say this section phi of Fu is lies in this filtration if this pullbacks of this phi under these two projections and take a difference. So this is a priori just section on U cross U extend to this section over dilatation. So this is definition, our definitions. And main result is actually under the existence of the smooth compactification, which is unconditional in case like a characteristic 0 or X is already proper. These filtration agree. That's the main result. And one amusing corollary of this is this actually this Abbes-Saito filtrations admits the functorialities like modulus transfer. Okay, which was the somehow like automatic for the motivic constructions. And I don't know if this has been known even for the classical case where F is G torsor. I just want that Takeshi knows if this kind of factorial was known for the case of the G torsors. Yeah.
Well, I didn't study this transfer, so I just need to know.
Okay, yeah. So I mean, but well, this gives some new. This could give us some new information of the Abbes-Saito filtrations, but also like it gives us some very effective tools to compute motivic filtrations, because Abbes-Saito filtration is much easier to compute. Okay, as you see in the following. But anyway, before going that, I mean, we just introduced characteristic form of the reciprocity sheaves. So which is basically like goes in exactly same manner as Takeshi's case. So let's recall the situations. So we are given some non-proper modulus pair where X is assumed to be smooth, and support of the this ramification divisor is simple normal crossings. And smooth D is a category of separate smooth schemes of finite type over D. And for reciprocity sheaves, now like exactly same manner as Takeshi's case, like we can construct the characteristic form as the the following map. So this is a map from the motivic filtrations at this modulus pair, and target space is the global section of this Kähler differential, sheaf Kähler differential with this twist, restrict D. And this is kind of a new part. And this is internal home in this category of the pre-sheaves on this category of smooth scheme over D from structure sheaf to the restriction of this reciprocity sheaf to these categories. And because like F was only defined on smooth schemes, you have to somehow make some effort to define it, but and first you define it on the category of smooth schemes over component, and also you can define it on the category of the smooth scheme on this interception component, and you just take this kernel of this standard map like this. And okay, this characteristic form, of course, I mean, turns out to be to the equal to the Takeshi's characteristic form in the case of the F is a group of G torsor for the finite abelian group. So this is kind of motivic version of the Takeshi's characteristic form, and well, construction is just done in the same manner as in Takeshi, and so this first two parts is almost same. So this is just you observe the this dilatation becomes vector bundles, and you look at this map. So first map is thanks to the our main theorem. So our motivic filtration is lies in this Abbes-Saito filtration, and by definition, Abbes-Saito filtrations, this pullback of the element over here to this U cross U extend to the dilatations, and you restrict to the this vector bundles. And you show this image lies in this additive part. And the last part is a bit different from Takeshi's case. But anyway, you can show this guy inject into this target space of our characteristic forms. Okay, any question so far? Okay, so then I state this main result on this characteristic form. So for this, we have this somehow motivic version of the Takeshi's theorems. So we have this characteristic form, and actually this characteristic form actually determine whether a given section lies in this this motivic filtration lies in a smaller filtrations. Yeah, so this is encoded in this injective to this map. So for any reduced component of this ramification divisor with multiplicity greater than 1 and then open subset, a restriction of the characteristic form to this open subset, kernel is exactly this like a motivic filtration for the smaller ramification divisor. Okay, any question so far? Okay, so now I move on to the okay. I mean some well, I elected some idea of the proof of these theorems, and which use some device to compute motivic filtration called like a reciprocity pairing. So take this like a proper modulus pair with interior U, and take this function field capital K over our base field K, and xk is just base extension. And for the coherent ideal I in OX, we have this relative Miller K sheaves on xk, which is locally generated by section of the form of the symbols, where first coordinate is congruent to 1 modulo I. So this was some Miller K sheaves used in Kato-Saito's classical theories. And some important fact we must recall is if IOU is OU, namely the support of I is disjoint from U, there exists some natural surjective map from the group of zero cycles to the this cohomology group. So these are dimensions, these are dimensions of X, and cohomology group of this Miller K sheaves induced by this local map for the cross point of UK. For the cross point of UK, adjusted resolution of the Miller K sheaves implies there's canonical map isomorphism from Z to this local cohomology, and you have this is a forget support map. Okay, so this local map induced this global map, and it's known that this is surjection. Okay, so then basic construction is the for reciprocity sheaf, there exists some bilinear pairing between the FU and this this inverse limit of the this cohomology group of this linear K sheaves into F of function field, satisfying the following conditions. So first condition is that if IR is ideal sheaf of R, and if you restrict this pairing to the subgroup of the those element, whose ramification is bounded by R, this pairing factors through this quotient here. And the second condition is if you consider the image of 1 over here, for a fixed close point of UK, this pairing is explicitly computed as this. So you somehow take this basic extensions, which is F element of F of UK, and you put it back to the F of Z by this closed immersions, and push it down to this F of K by this finite one. And so by the surjectivity of this map theta here, and this two conditions characterize this pairing here. So issue is existence of such a pairing. Okay, and so here's the example. So if F is a dual of the abelianized fundamental group, and our base field is finite, and F of K is canonically isomorphic to the Q over Z. So our pairing, where capital K is our base field, induce the map from the this projective limit of the cohomology group of the linear K sheaf to the dual of this H1U, which is a abelianized fundamental group of U. And actually this coincides with a reciprocity map in the higher dimensional classical theories of Kato and Saito. And also, if F is a group of the connection, rank 1 connection, and X is curved, actually this pairing has been considered constructed by Bloch and Noth. And in their study of the Gauss-Mann indeterminate for rank 1 connection curves. And our construction gives some generalization to a higher dimension. Okay, any questions so far? And I just give you one word on the construction. So this construction, I cannot give too much about it, but I just say one word. So this construction of this pairing use the push forward map for the reciprocity sheaves. So namely, any given proper morphism of the smooth schemes, Venus ruling myself construct some proper push forward map of this form, where f of x is a restriction of f to the small Nisnevich side, and f of d is sort of the Taito in the context of the reciprocity sheaves. Okay, and this construction actually recovers the Grothendieck push forward map for the cohomology of the Kähler differential, and also push forward map for the cohomology of the Durand-Pitt. Actually, we don't need to use the general machinery of the Grothendieck duality or Kähler dualities for this construction. Okay, any question? Okay, so then I have to state this some main result on this some computational tools of the motivic filtrations, but actually for this we need more effective kind of computational tool, which is induced by this reciprocity pairing. So let's recall this situation where we have some proper modulus pair and use the interior as case function field, and we had some reciprocity pairings between Fu and some project limit of the cohomology group of the linear K sheaves, but this pairing induced some local version called higher local symbols, which looks like this. So this is a collection of the pairing indexed by the set of the sequence chain of their points on X capital K, where Xi is codimension I, and closure of Xi contain Xi plus 1. And this OA, this guy is the handelizations along this, like a chain of the points. There is a way to handelize this scheme X capital K along this handleization, which somehow that goes like a first handelize Xa at this close point, then you just handelize these schemes on the pullback of this next point, and so on. That you go on like this, and you get some finite product of the Hengelian DVR. And this is a total quotient ring of the Hengelian these things, and which is finite product of the Hengelian discrete variation field, and this is Milnor K group of this kind. And this global pairing, reciprocity pairing, induce this kind of a local pairing indexed by this chain of the points. And so this is main computational result of the motivic filtrations on the reciprocity sheaves. Okay, so assuming this, like X is nice, so smooth, so X is now smooth and proper, and this ramification divisor support, so is simple normal crossings, then this element of Fu lies in this motivic filtrations at this R. So ramification of A is bounded by R if and only if A annihilate this higher unit group of this Milnor K groups for all function field and for all sequence of points. Because this is really like a very concrete group, like generated by symbols, some very modular some Steinberg relations, and this gives us a very effective tool to compute these filtrations, motivic filtration. So I just give some one word for the proof of these theorems. So implication from 1 to 2 is almost definition. And the other implication is somehow it follows from the factorization map theta. So theta was mapped from the group of zero cycles from zero cycles on UK to this cohomology group of the relative Milnor K shifts. And we had, so this guy is identified with the K point of this representative object. And we had this quotient of this guy attached to this pairs, and which was used to define this motivic filtrations. And the K-value point of this guy is identified with the Serre group with modulus. And the point is to construct this map here, which factorize this map theta. Okay, that's all I can say. And then idea of the proof of the comparison of the motivic filtrations and Abbes-Saito filtration is okay, given some section A of F over U, we can apply the projection formula of this higher local symbols to this setting for this dilatation, and we use above theorem, these theorems, and then to compare the ramification of this A along this boundary and the ramification of this difference of the pullback along this boundary. That's the basic idea of the proof. Okay, any question? Okay, so then I'd like to move on to some examples of the characteristic forms. So here we assume X and D is smooth, D is closed subscheme, and our ramification divisor is n times D. X is now affine, and D is defined by this pi equals 0. And bit vector case, this is actually, like recovers this, okay, so in this case, this motivic ramification, motivic filtration on the bit vectors of the length S actually recovers the filtration considered by Kato-Russell, which is Frobenius saturation of the Bryansky-Kato-Matsuda filtrations. And characteristic form in this case is computed as exactly by the same way as in the case of the situations of the G torsors. They actually this include some expressional case where P is 2 and N equals 2. This computation, okay, so where this, this guy showed up in the first sections. This is a refined Swan conductor considered by Kazuya Kato's. And okay, so this guy is iterative this fair theorem from O to the WS. And that's the case of this case. And this expressional case, you have to add this term over here. And this is given like this. This map is given by this multiplication of the residue class of this pi square times A0. A0 is the first component of this vectors. And this is the Frobenius. And this computation is due to Yatagawa. Okay, that's the case of the bit vectors. And this actually, okay, induce the computation of the case of the G torsors using this Attenborough-Schreier bit by this commutative diagram. So you have this, because of this, this characteristic form is functorial. So you have this commutative diagram. And the point is this, this map induce surjection on the motivic filtrations, and which is highly non-trivial. And this is not the case in general. For example, if you take here W tilde S minus 1, then this is not surjective anymore. So, I mean, somehow you have to really show the surjectivity of this map. So then you can prove that this characteristic form of the for the this G torsor is computed exactly same as same manner as in the classical case. Okay, so this doesn't give us anything new. But now we move on to the Kay differential. So this gives us something new. Okay, so we take this Kay differential, which is reciprocity sheaves, and you take this ramification divisor n times d. D is smooth. So our characteristic form, recall that this looks like this. So this map from the motivic filtration of the Kay differential to this these things. And okay, by using computation of the characteristic form, you can show this motivic filtration on the Kay differential is given like this. For a case characteristic 0 or P not dividing L, this is given by, as you may expect, this is a log form with this pose along D. But if characteristic is positive, dividing n is this multiplicity, then you get these things as motivic filtrations. Okay, and then actually furthermore, this map characteristic form factor through this kind of map, where this C is mapped from this guy to this guy given by this this formula. Actually, this turns out to be an ODO homomorphism from this guy to this guy, where all module structure on this is given by left multiplication on this structure sheaf. Okay, so we are now reduced to compute this map. And actually, this is given as follows. For this, we need to introduce some notation. And we have this subsheaves of this guy generated by this section over d pi or pi to the n, which we can easily show the independent of the choice of pi, defining equation of d. And you have also the residual map with this twist by this formula, where this residual d here is a usual residual map along d. And this also is independent of the choice of pi. So using this guy, we can compute this map as follows. So for this case, this quotient of the motivic graded quotient of the motivic filtration is identified with this quotient, and this is turns out to be isos with this is a d pi over pi to the n tensor this guy by this regional twisted regional map, and also composite of the differential and twisted regional map. And here in this case, like we just see only one component, and this is a quotient, graded quotient of the motivic filtrations, and which is now modified to the this guy by twisted regional map. And but actually, more interesting case is this case. So positive p is a positive dividing n. So then this our map actually induce injection, but it's not so easy to describe the image of this map. And for simplicity, so we assume that these are affine space and X is a product. And for example, if you take this kind of form of this form, and over here, so this gives you okay, this gives an element over here, section of this over here, where f is a polynomial. Then this character form is computed as follows. So which somehow seems complicated and involves some partial derivative of these polynomials and so on. And I couldn't find a way to give this any sensible geometric interpretation. And it's kind of surprising that this kind of apparently very artificial formula, which seems to dependent of this coordinate, comes from some really natural global map. Okay, any questions so far? Is it okay? Okay, in the last 3 minutes, I just application of the result I mentioned to the some descent for the reciprocity sheaves. So let's LK to be some left kind extensions from pre-sheaves on category of smooth schemes to the pre-sheaf of the category of the whole schemes. And this is the joint work with the Kay Saitos, Shane Carey, and assuming characteristic 0 or embedded resolution singularities, CDH sheafification of this left kind extension of the reciprocal sheaves satisfy the so-called CD arc descent. So this, this topology, I mean, okay, so was first introduced by Butt and Matthew, and its CD version was introduced by this Elmont, Hoyoiwa, Iwasa, and Kelly, and I just recall the definition. So QCQS morphism of schemes is a CD cover if this map like this induced map is surjective for all Henzelian variation ring of rank less than 2 equal 1. And it's kind of like amusing that ramification theories has such as application to the some descent result. Actually, this this topology, this CD arc topology is much stronger than CDH topologies, and somehow it's kind of surprising that CDH sheafification of the reciprocity sheaves automatically satisfy descent for such a strong topology. And okay, so just I'm just running out of time, so I just gave this ingredient of proof. So this theorem follows from the following theorems, which actually follow from the Abbes-Saito formula for the motivic filtrations. So this is a brilliantly cut formula for the motivic conductors. So let's scale it to be a function field over our base field. X is regular separate of finite type of the function field, and take this K rational point, and D is a regular divisor containing 0, and C and C prime is regular curve intersecting transversally with D at 0, but C and C prime may not intersect transversally. And we have this associate this Henselian discretization variation ring. This is a Henselization of the X at the generic point. This is a Henselization C at this 0 rational point, and so on. And then if for given some section of X minus D, you can restrict to the C minus 0 and the C plus minus C prime minus 0. And then if, so this is how motivic conductors in induce defined by using motivic filtrations on these, the value of the F tildes on these Henselian variation rings. So this guy satisfies these formulas. If this intersection multiplicities of C and C prime at this rational point is greater than equal to the this motivic conductors of this A, original A on this for this Henselian discrete variation ring, then motivic conductor of this restriction coincide. Okay, that's the okay. So I just wrote this definition of motivic conductor, but I just because actually I just want to say all this kind of a phenomena has been observed by Kazuya Kato before. I mean, in a long time ago in papers, in his papers on some D module and stuff. Yeah. Okay, that's it. Thank you very much.
Thank you for very nice talk. Are there any questions?
Yeah. Okay. Let me ask one question. So, so you have this characterization of this filtration in terms of pairing with Milner K group.
Yes.
So this reminds me that the definition by Kato-san on the abelian quotient of absolute Galois group. So
yes.
So in his setting, so in first he studied the higher local field, but then he generalized it to arbitrary Henselian discrete variation field. By considering pairing and so to study character of Galois group, so you take pairing into the Brouwer group. Studying Brouwer group, Kato-san defined the filtration.
Also, yes.
So is there something similar in this
yes, because like Brouwer group is also reciprocity sheaves. I mean, you have some motivic filtration on this Brouwer group, and its characterization by this kind of a local symbols. And okay, well, I have to confess, like I didn't compute it. I mean, but Kato-san, I think that I think that Kato-san somehow considers a logarithmic version of this. Yeah, and Kato-san even consider this higher the unramified cohomology in the higher degrees, and also define this like a ramification filtration by using this kind of a pairing with Milner K group of the higher local fields, but now like I think this I use the filtration I use. This is a kind of a non-logarithmic filtration, higher unit groups. And Kato-san used a logarithmic higher unit groups. so somehow this motivic construction gives us non-logarithmic this version of the Kato-san's filtration. Yeah. So, and also like I also thought about this like the case of the general Hengelian variation rings, and I have some idea to somehow formulate this, like this case in this framework, but like I didn't have enough time to just to make this precise so far. Like, but this is certainly, I mean, interesting problem to study. Yes, I agree.
I see.
Yeah.
Okay. So this gives me another question. So so in this abelian character case, so we have logarithmic filtration and non-logarithmic filtration.
Yes.
But so cohomologically, so first Kato-san defined filtration, and then Matsuda-san modified.
Yes.
But this modification is found only in characteristic P. So in mixed characteristics, we don't know how to modify Kato-san's filtration. So is there a method to give you some?
I mean, these things like okay, recently Kelly and Miyazaki launched some like a project to extend this theories over any general base. And well, I mean, well, it would be really nice to extend all these theories over a general base to handle the mixed characteristic case, and also, of course, and actually, their theories even work for the non-abelian situation. And so I wonder. I mean, I just don't know how far we can go, but like there is some hope to go on with this framework and extending this abelian situation of a field to the non-abelian situation over general base. And but like this will take some time.
Thank you. So my last comment is not a question, but just a comment. So you have this definition of modulus transfer, and you get some inequality in the definition. And this condition is exactly appears in the condition. So I proved the stress formula for.
Do you mean this formula?
No. Much in the definition of modulus transfer, so you restrict it to curve, and you find some inequality of divisors.
Yeah. Okay. This one, right?
I don't see that inequality. Inequality. You have the divisor and the pullback to curve, and you compare. So you have two factors, x and y, and r and s and.
Yes.
Yeah. So this condition appears exactly in my proof of Torres formula for left set Torres formula for open variety.
Yes.
So do you see some intrinsic reason why the same thing appears?
Yeah, I mean, I don't know. I mean, like it's somehow okay. So what I can say, I mean, somehow like everything starts from here. Actually, like this, like a definition of the our motivic filtrations, it's really starts from here. Like we somehow use this restriction to the curve, and there you just look at this like ramification conditions, right? And then everything what I talked about this today is start from here, and then somehow it recovers. I mean, surprisingly, the your filtration on the for the torsors, and of course this says something more than what I say today, but I cannot make it precise at this moment. Like I have to like look at this like more closely, and but of course like yes, you are right. I mean this is really a crucial kind of conditions. which we use to define the motivic filtrations on our motivic filtrations. Yes, yes, yeah.
Yeah, thank you very much. So thank you very much for the beautiful lecture.
Thank you. Yeah.
Professor Kato, please.
Yes.
Okay. Hi. So is it possible to use harmonic varieties with modulus in this story? Harmonic varieties with...
Yeah, I mean, somehow, okay, that's somehow the consequence of this story. And yeah, actually, you have mapped from this Char group of zero cycle modulus to the harmonics with modulus, which you defined. And but this map has, in general, a huge kernel. So I mean, somehow like harmonics with modulus cannot control the motivic filtrations. But I wrote some paper with Binder and Merich, where I show for the one motives. For the one motives, you harmonize with modulus somehow control ramification. So if you restrict to the one motivic part of the reciprocity sheaves, then you are harmonize with modulus control the ramification.
Hi, thank you.
Yeah, so if you're interested, you please look at this my paper with Binder and Merich.
Hi, thank you.
Miyazaki-san, please.
Thank you very much for a beautiful and nice talk. So I have only one question. So I'm recently interested in the relationship with the motivic ramification on higher dimensional variety and its restriction to curves.
Yes.
Did you hear me? Sorry.
Yes.
I didn't call.
I don't see you. But I don't see you.
So sorry. Yeah. Excuse me. My shirt is not so very beautiful, so I didn't want to show you. But yeah. Anyway, sorry. Yeah. Thank you. And so do you expect that you can? To my understanding in ramification theory, usual ramification theory, there is a result something like you can characterize the ramification by restricting to the curves on the varieties, right? And do you expect the similar thing for reciprocity?
Yes, it's already it's already written in the framework of the motivic conductors in my paper with Kai.
Really?
Yes.
Really?
Yes. Yeah.
So is it true that it's?
No, I mean, well, in general, it's not true that this ramification is determined by the restriction to the curves, and we somehow introduced the this. So conductor, conductor is level of the conductors, and and levels tells you how big dimensions you need to determine these ramifications after restrictions. And so there are hierarchy of the reciprocity sheaves by levels by this properties. And so I mean, but actually the nice things about this is once you start, you're given some kind of reciprocity sheaves of level 1, which means this ramification of the reciprocity sheaves determined by the restriction to the curves. There is some canonical extension. So once even if you started from some conductors or conductor only defined on the curves, which means a Hengelian discrete variation ring with perfect residual field, there is a way to extend it to the the conductors on the Hengelian variation ring with generous base residual field. And so using this formalism, there is some way to extend in a canonical way some conductors only defined on the perfect residual field case to the general residual field case. But anyway, so there are some hierarchies of the reciprocity sheaves by these properties of the restriction to the some subvarieties of the
I see. Thank you very much.
Yeah.
I will look at it. Thank you.
Yeah.
Are there any questions or comments? Thank you, speaker, again.
Thank you very much.
And do organizer have any announcements?